Alright, so we got particle kinematics for chapter 11. Here in this first problem, we are given the motion of particle relation. So we're given the position function of x equals 6t to the fourth minus 2t cubed minus 12t squared plus 3t plus 3. And we are asked to determine the time, position, and velocity when acceleration is equal to 0. So as we have the position function, to find the velocity and the acceleration, we take the first and second derivative to find those respectively. Therefore, we get the velocity function as 24t cubed minus 6t squared minus 24t plus 3. And our acceleration is 72t squared minus 12t minus 24. Going at setting the acceleration equal to 0, we use the acceleration function, and we were able to find t at two-thirds seconds. Plugging that back into our position and velocity equations, as that is what we were asked to find, we were able to find that the position at two-thirds seconds is 0.259 or 0.26 meters, and our velocity at two-thirds seconds is negative 5.6 meters per second. Moving on to the second question, we are given a picture of a bullet going into a resting medium with an initial velocity of the bullet at 900 feet per second. The bullet then travels a distance x of 4 inches before coming to rest. We use the equation v equals v naught minus kx. We are asked to find the initial acceleration and also the time required for the projectile or the bullet to penetrate 3.9 inches before coming to rest. So using that first equation, v equals v naught minus kx, we are able to find k, plugging in our values, that k is equal to 2,700 seconds. Then using that information to move on to part A to find the acceleration of the projectile, we use the velocity equation, take the derivative of that, and we are left with minus k times v, which is then negative 2,700 times v. And our velocity equation is, again, v naught minus kx. So we're able to plug that back in and get our acceleration at 0, which is negative 2.43 times 10 to the 6th feet per second squared. Moving on to part B. So we have the velocity, and we do a separation of variables, thus getting our time on the left side, and we take the integral of both. We take dt from 0 to t equals the integral from 0 to x of 1 over v, or v naught minus kx, with respect to dx. Using a quick u substitution, we have 1 over u, the integral from 0 to x times 1 over u du. And from there, we can find that our time, the time equation, is equal to negative 1 over k times the natural log of v naught minus kx, evaluated at 0 to x. Plugging those in, we're able to get this final equation. So our t is equal to 1 over k, or negative 1 over k, which k is equal to negative 2700. So we have 1 over 2700 times the natural log of 1 over 1 minus 2700 over 900 times 3.9 inches divided by 12 inches. This gives our time, the time required, as 1.366 times 10 to the negative 3 seconds. In this third question, we are given the expression a equals 10 minus 0.8 v. Our v naught is equal to 16.5 feet per second. The ball that was dropped takes 3 seconds to reach the bottom of the lake. We're asked to determine the depth of the lake, and the speed of the ball when it hits the bottom. So going off of our free body diagram, and using what we know, we use a separation of variables to with respect to time. So we take the integral of dt and our acceleration, much like we did in the last problem, and we are able to get our t is equal to negative 1 over 8 times natural log of 10 minus 0.8 v, evaluated at 16.5 feet per second squared, or no, feet per second, sorry, to v. Evaluating this out, we are able to we're able to solve for v, continuing to use the equations that we learned in calculus, as the natural log goes away by multiplying it by e to the x. So using that, we're able to find our v equation is equal to 12.5 plus 4e to the negative 0.8t. Then using that equation, again, deriving it, using again another separation of variables, able to follow the same process to get a position function of 12.5t minus 5e to the negative 0.8t evaluated at 0 to t. Using this equation, at t equals 3 seconds, we're able to plug in the values and find that the depth of the lake is 42 feet. Using the velocity equation, we plug the t equals 3 seconds in there as well to find the velocity of the ball when it hits the bottom of the lake, and plugging that in, our velocity is 12.86 feet per second. Right. The next problem, we are given the function v equals 7.5 times 1 minus 0.4x to the third, to 0.3. X is equal to 0, t is equal to 0, and we are determining the distance the jogger has run when time is equal to 1 hour, the jogger's acceleration at t equals 0, and the time required for the jogger to run 6 miles. Much as we've done in the last two, we use separation of variables to get our t function as we go through, using a u substitution and evaluating it at 0 to x. We are able to find that the position our x is equal to 1 over 0.04 times 1 minus 1 minus 0.21t to the 1 over 0.7. Plugging this time, the time is equal to 1 hour, in, we find that the distance, x, is equal to 7.1 miles. Continuing on for part B, we again use a separation of, no, we do not use a separation of variables. We're able to use this and take the derivative of this original function. Solving that, we're able to find that the acceleration is negative 0.675 times 1 minus 0.04x to the negative 0.4. And using what we know at t and x are equal to 0, we're able to take the negative 675 miles per hour squared, multiplying that using the unit conversions, we're able to find that the acceleration at t equals 0 is negative 275 times 10 to the negative 6 feet per second squared. Using part of our equation that we found in part A, we take 0.21t equals 1 minus 1 minus 0.04x to the 0.7. Solving that for t and plugging in 6 miles for x, we're able to get that our time to run 6 miles is 49.9 minutes. On to the next one. We are given the function a equals negative g times r squared over r squared. So capital R is equal to 3,960 miles. Our velocity is equal to 0, and our lowercase r is infinity. So we're asked to calculate the escape velocity of this, again using separation of variables. We are able to find that our escape velocity is equal to the square root of 2g times capital R, which in this case, g is equal to 32.2 feet per second squared. And we know that our r is equal to 3,960 miles. Using the unit conversion, we're able to get it in feet per second squared. Thus being 36.7 times 10 to the third feet per second squared. Moving on, we have a pulley system, or a cable system. And we are asked to determine the accelerations of handle A and weight B, and the velocity and change in position of handle A after 0.5 seconds. Taking the free body diagram and using similar equations that we used in one of the examples from the videos, we're able to find our equations. And plugging in what we know, that VB is equal to 2 feet per second and YB is equal to 4 inches, we're able to find that the acceleration of b is equal to 6 feet per second squared up in the positive direction, and acceleration of handle A is 18 feet per second squared to the left. Using the equations, v equals v naught plus at for part B, we are able to find that the velocity at A is equal to 9 feet per second, plugging in the values that we found in part A. Then using the change in position function of delta xa is equal to ax naught plus va naught times t plus 1/2 acceleration a times t squared. Plugging in these values, we're able to find that the change in position at A is equal to 2.25 feet to the left. In this question, we have a parachuter falling at 200 kilometers per hour. He opens the parachute at 600 meters, and he has constant deceleration of 50 kilometers per hour from 586 meters to 30 meters. So we were able to draw our graphs, and finding the area underneath, we were able to solve this problem. So A, as we look for the time, the total time for the parachute is to land, as we take our height equal to negative t times our velocities in meters per second, divide that by 2, we're able to get t1 is equal to 0.4032 seconds. Following a similar pattern at t2, using the graph from 586 meters to 30 meters, we are able to find that t2 is equal to 40.03 seconds, as it is a constant drop. And then for t3, using a similar equation, we're finding that t3 is equal to 4.32 seconds. Thus, adding those up, our total time is equal to 44.8 seconds. Part B, for the initial deceleration, we take negative 13.888 meters per second minus a negative 55.555 meters per second. Dividing that by t1 as our initial time, we find that the initial deceleration is 103.3 meters per second squared. The next one, this one was a little bit tricky, as I needed to go through my Calc 2 to really get this correct. Going from our initial equation, we're asked to determine the magnitude of velocity and acceleration of the particle. So we need to take the derivative of this and find both the acceleration and velocity. Here we are finding the velocity function, and through all of this we are able to find through constant we're able to find that our velocity function is equal to the square root of r squared times 1 plus omega n squared t squared plus c squared. And then using our acceleration, the acceleration function, we are able to find that our acceleration is equal to the square root of capital R squared times 4 omega n squared plus omega n to the fourth times t squared, or capital R omega n times square root of 4 plus omega n squared times t squared. In this next one, we have a slow pitch softball. And we were given our conditions that the ball must be between 1.8 meters and 3.8 meters for its maximum height. Initial velocity is 13 meters per second, and our alpha is 33 degrees. We know that our y naught is equal to 0.6 meters at distance of 0, and the ball is traveling a distance of 15.2 meters. So to find if the pitch meets the height requirement, we use Vy equals V naught sine alpha minus G times T, plugging in what we know and solving for T to find the time. We get T equals V naught sine alpha over G. Using that, we find that our time is equal to 0.7217 seconds. Plugging this back in on our known values for the max height, we use the equation y naught plus V naught sine alpha times T minus 1/2 of gravity times T squared. Plugging in all of our known values, we get that the max height is 3.16 meters, which meets the requirement. To find the height of the ball as it reaches the batter, we use the function x equals x naught plus V naught cosine alpha times T. Once again, solving for T, we get 1.3941 seconds. Plugging this back into a similar equation, we get that the height of the ball is equal to 0.938 meters. Here on the next question, we have souvenir balls thrown into the stands at between some distance. We're asked to determine the range of values of V naught if balls are to land between 10 meters and 17 meters. So using what we know as our theta is equal to 40 degrees, y naught is 2 meters, and our position is equal to 0. We have the functions Vx naught and Vy naught equal to V naught cosine theta and V naught sine theta. Using our position function of V naught plus Vx naught times t, we're able to solve for our time function. And we are also can use that we can solve that for our time function, which our time is equal to 1.305 seconds. Using these x equals x naught plus Vx naught t, actually no, using the position functions in both the x and y for points B and C, we're able to get our values that we need for our velocities at B and C. So plugging those in For point B, we find that V naught t is equal to x over cosine 40, which we get from 8 plus 10 cosine of 35 degrees, as that is how the stand is elevated, and we get 21.1365 meters. Plugging this back in to our V naught equals x over t, our V naught b is equal to 16.2 meters per second. Following the similar approach, we're able to find that our V naught c is equal to 21 meters per second, and that is our answer. And using, for the next problem, we're asked to determine the velocity. Using what we covered in lecture, we have an equals VA over rho. Plugging in our values, we get our acceleration at 12.13 meters per second. Again, similar in the next question. Airplane traveling at 240 meters per second. We have the equation of max acceleration at equals v squared over rho. Plugging in our values and manipulating the equation to find rho, we find that rho is equal to 1467.9 meters. And here, using what we know, we can plug in our values, find what we need to. Sorry, I'm rushing through this because I have to submit this in 5 minutes. We find that our R is equal to 57.9 feet per second squared, and our V is equal to 370 feet per second, and our theta dot is equal to negative 0.0924 radians per second. Plugging this all in, we get what we need. And the last question, similar to the pulley system that we did earlier, and we use the same type of approach as we have our constant equations and our known values. We get the acceleration of B is equal to 240 millimeters per second squared. The velocity of A, or acceleration of A, is 345 meters per second squared. For B, velocities of A and C, velocity of C is equal to 130 millimeters per second, and our velocity at A, using time 2 seconds, is 43.3 millimeters per second. For C, the change of position, we use a similar function that we've used earlier, and plugging in our values, we find that our change in position at C is equal to 728 millimeters. Thank you.